So let's go for the next part of this lecture, and this is important. This is a very important part of the theory, and it concerns the fundamental theorem of integral calculus, which is one of the most important results that we will prove here. And one of the most important results of the analysis, because it opens the road towards the computation of areas of integrals, which is the main problem we treat this year. So, first of all, let me give you a definition. We have a function f whose domain is AB and whose target set is R. This is integrable. Since it is integrable, it is possible to define a function f, capital F, from AB to R, that associates to every x the value f of x, which is the integral from a to x of f. Here I write the variable t, not x. Why? Because x is already present here. Okay, so it would be somewhat strange to use the same variable. When you perform an integral, the variable here disappears. This is just the variable like the index in sums. It is not present at the end. But here x must be present at the end. And this is called the integral function. Of small f. It is it is immediate to represent the function capital F given small f. So here you have a function, for instance, like that. I'm sorry. Here. And the left extreme of the interval is A, the right extreme of the interval is B. And if you consider x here, the area between the graph of the function f, small f, and the interval AB, so this purple area here, is exactly corresponding to this integral, so it is capital F of x. So this is capital F of x. And another remark. Is the following. Since capital F of B is exactly the integral between a and b of f, here I can call it x at the end, the variable. It is not important here. This is just a number. So I can call here the variable inside the integral how I want, y, x, t, w. Okay, since there is this equality, so the problem of computing the integral or the area corresponds to the problem of computing the value of the function capital F at the point B. Okay? This is the remark. This is just a question of language, nothing changes. Okay, but now what we are interested in is computing f of b, or knowing the function capital F. Now there is an important notation to introduce. Here, I recall you that we just studied the functions from AB to R with A less than B, and both A and B finite, and F integrable. And we just introduced this symbol, the integral of F from A to B, where A is less than B. We define now the other symbol, the integral of the same function f of x dx, but not from A to B, but from B to A. And just by convention, we say that this is the same, but with minus sign. Okay? Take it as a definition. In the context of analysis 1, this is just a definition. More advanced context, it is a particular case of a more general rule that is more justified. For us, it is just a definition. And it is quite comfortable as a notation, as a definition, because we can remark the following fact. Namely, that for every triplet of points A, B, C in R, irrespective of the ordering of A, B, C, which one is the largest, which one the smallest, which one of the three is the intermediate point, we have that the integral from A to B of the function f is equal to the integral of the same function from A to C plus the integral from C to B of f. This is exactly the rule that we proved as the last rule of our algebra. Okay, very, very natural. But in our algebra, we require the C to be the intermediate point between A and B. Here it holds for every A, B, C. Let us try to understand how this can work, and so let us compute some examples. As a first example, take so you in principle should cover every case, but if I show you one case, I think it will be sufficient. Okay? So, from the third rule of the algebra, we know our starting point we know that the integral between B and C of f of x dx is equal to the integral from B and A f of x dx plus the integral from A to C f of x dx. Okay? Here we did not use our new convention, our new definition, because here we took just integrals from the lower point up to the upper point of an interval. A very standard way. But now, so here we have the integral between A and B that corresponds to this. So we move this on the other side. So we have this is equivalent to say minus integral B A f of x dx is equal to AC f of x dx minus integral BC f of x dx. This is just, I would say, arithmetic. This is just very, very elementary algebra. We still did not use our definition, but now we use the new definition. And then reverse the integrals with minus in order to obtain plus sign. So here we have minus BA becomes plus the integral between A and B, equal to the other integral from A to C. This is already with a plus sign, so it is to be left untouched. And the last one, integral between B and C, we put a plus in front of the integral, and we end up with the integral between C and B. And this is exactly the rule we aimed at proving. Okay? So as a homework, cover the other cases. Indeed, can be made in various ways, smart ways to exploit this, and just changing the labels, changing the names. However, compute all other cases. The important fact is that now, by this definition, this simple rule holds irrespective of the ordering of the points of the triplet A, B, C. And now we are ready. We are ready for the fundamental theorem of the integral calculus. Okay? So, how do you say when you, with drums make something like, okay, here we are. Fundamental theorem of integral calculus. So we have the following statement, okay? I write here again, fundamental theorem of the integral calculus. And it is the following. Consider a function f from a, b to r. Continuous, very important. The function that we discuss in this theorem must be continuous at every point. So continuous in AB, which means at every point of the closed bounded interval AB. Then again, the integral function capital F of x is defined as before. Then for every x bar in AB, we have that f of x minus f of x bar, capital F, is equal to what? To small f of x bar times x minus x bar plus little o x minus x bar for x going to x bar. Or, equivalently, formulation is the same, the limit for x going to x bar of this strange ratio capital F of x minus capital F of x bar divided by x minus x bar is equal to small f of x bar. Okay, let us stop 1 minute before proceeding with the proof, because I think now it is quite difficult to understand the importance, the relevance of this formula, so I want to stress it. Remember that in our problem, computing the area under the graph of f is the datum of our problem. This is what we know. The problem is finding capital F. There is a link between small f and capital F, but this link is very mysterious. It is not clear at all. Capital F is just the area below small f. But functionally speaking, what is the link that we are looking for? This is extremely difficult to understand. But this theorem gives us a strange formula. It says that there is a link. And the link is that if we perform this limit on capital F, then we find small f. And notice that this is much simpler. This is much simpler because here we have something easy. It is quite easy to have here. It is quite easy to have here a limit to be computed and not an integral. Integral is difficult, limit is easy. We already know how to move with this sort of problem, with the problem of computing a limit. So it is a huge simplification of what we have to do. And geometric pictorial interpretation A pictorial interpretation is the following. So here we have AB, and there is some graph here from A to B. And so now look at this formula here. Capital F of x. If here we have x, and here we have x bar. So what happens is that capital F of x is equal to the area under the purple graph between A and X. This is the area. On the other hand, F of X bar is the area between A and X bar. So it is clear that the difference between the two, F of X and F of X bar, is the area here. This green is capital F of X minus capital F of X bar. Okay? Now, what is saying this formula, the integral? That this area here is equal to F of X bar times X minus X bar. What is F of X bar times X minus X bar? Let's consider this new color here. This is F of X bar, and this interval is here is X minus X bar. So the first term here, second member, right hand side of this equality, is this blue area. So the formula says that the difference between the green area here and the blue area here is Lido law of X minus X bar. But what is this Lido law? What is this area? This difference is simply this one in gray. This part here and this part here. Okay? This gray area is Lido law of X minus X bar. What does it mean? Okay, it means that it's negligible, and we can see that it is small. But the Lido law is not only to be small. It means that it is infinitesimal with respect to the other. as this f of x minus f of x bar, so as this area goes to 0 when x moves towards x bar, also this gray area goes to 0, but it goes faster. It is an infinitesimal of higher order. And indeed, let us try why, to understand why. First of all, it is not a regular region, okay? But if we go closer and closer, it may seem to be a regular region, a sort of triangle. This triangle has a basis, which is x minus x bar, and this basis goes to 0 as x moves towards x bar. Okay? So, and this goes to 0 and brings to 0 this area of this rectangle, f of x bar times x minus x bar. It brings to 0 also the gray area. But this is not the only reason why the gray area goes to 0. The other reason why the green area goes to 0 is that also the height of this sort of curved triangle goes to 0. And the fact that the height goes to 0 gives you the lead law. If it is only for this side that goes to 0, this is the same for the rectangle and for the gray area. But the gray area has another reason, which is the fact that the height goes to 0. It seems to be elementary, but it is not, because the fact that the height goes to 0 requires the continuity of the function. Because otherwise, if there is a jump here, a jump at x bar, the gray area would not go to 0, but the continuity forbids jumps and then gives the gray area another reason to go to 0. And this is the reason why the theorem holds and requires the function to be continuous. But let us go to the proof, because we believe mainly in proofs. Okay. So take a point at random, whatever point you want, x bar, a point in AB. And x be a point in the closed interval AB. So f of x minus capital F of x bar, by definition of integral function, this is ax f minus ax bar f. Okay, here we could proceed geometrically and write immediately the result, but I prefer to proceed algebraically here, and just to say that here we have ax f of t dt plus x bar a, so here I changed the order of the extremes of integration, and here we are exactly in the situation where there are two extremes and an intermediate point that is repeated, and this is the rule that we proved before. This is why we proved it before, because there is no order in x minus x bar, in x and x bar. So we have to be more general, but at the end we can write this is the integral between x bar and x of ft dt. Okay. Now we have to prove limit here, and a nice way could be to use sequences. So let xn a sequence in AB such that xn converges to x bar, then we have that capital F of xn minus capital F of x bar, according to the formula we found here, this is equal, to the integral of f between x bar and xn. This is f of t dt. Now, since f is continuous, then by mean integral theorem, by the theorem we proved in the previous video, this is why such a theorem is important. There exists a point Cn which is between xn and x bar, but since we don't know whether xn is before or after x bar, as we already did, we write this. Cn is in xn x bar when x bar is larger than xn, or x bar xn when x bar is smaller than xn. The union here provides exactly what we want. So here, such that integral average theorem, f of Cn is equal to x bar xn f of t dt, so the average here, divided by xn minus x bar. And remember in the previous writing with the integral function, this is capital F of xn minus capital F of x bar divided by xn minus x bar. Now, since f is continuous, here we use continuity at the end, and we have that xn less or equal Cn less or equal x bar, or x bar less or equal Cn less or equal x, or more generally, zero is less than x bar minus Cn less than xn minus x bar. By put it as you want, this goes to zero, so by two policemen, so double comparison theorem, we have that Cn goes to x bar and f of Cn goes to f of x bar by continuity of f again. Therefore, from the relationship asterisk, we take the limit for n going to plus infinity, we have from one side here f of Cn goes to f of x bar, and this is equal to the limit for n going to plus infinity, capital F of xn minus capital F of x bar divided by xn minus x bar. And now we apply the limit through sequences theorem that says that for every sequence such that xn goes to x bar, there is this equality, so it is the first, the easy part of the theorem. Tell us, oh, not sorry, it is the difficult part, the second. LTS tell us that this implies f of x bar is equal to the limit for x going to x bar of capital F of x minus capital F of x bar divided by xn minus x, x minus x bar. Okay? And so This is the end, but we can also observe that equivalently f of x minus f of x bar divided by x minus x bar is equal to f of x bar plus Lido law of 1 as x goes to x bar. And here, f of x minus f of x bar is equal to small f of x bar times x minus x bar plus Lido law of x minus x bar as x goes to x bar. This is the end of the proof. And now we are done. Now the program is easy. Now if you really realize what we did up to now, the program now is easy. Because the program just says the following. Now, given f, compute the integral, namely the integral by the limit we wrote here, f of x bar is equal to the limit for x going to x bar of capital F of x minus capital F of x bar divided by x minus x bar. Okay. But what is the problem? The problem is that this is not a limit. This is a much more complicated problem because here we know the result of the limit. In the problem of computing the area, we are given small f. And we don't know capital F. So this is a sort, so be careful. It is not so simple. This is a sort of inverse problem of inverse limit. When we have to compute an integral, we are given the result of the limit. We are given small f, and we aim at finding capital F. Of course, this is a difficult problem. Think of the following problem. You know that the limit is 2. What is the function? Of course, this is strange. It is quite difficult to give an answer like that. The problem is not so ill-defined because here we don't have just a function. We have this strange ratio that we will call incremental ratio because it is the ratio between the increment of the function and the increment of the variable. So it is not a free function. It is a structure a bit more rigid. It will help us. However, if you are smart enough, you immediately see that this problem has infinitely many solutions. Because if instead of a capital F here, we have capital F plus 1, this gives, again, this plus 1 cancels here, and then the result is the same. So the problem of finding capital F given small f has infinitely many solutions. But this will be not a big issue at the end. However, now the problem is the following. Study this problem here. Study this problem here, which is not, again, computing a limit, but finding capital F such that this limit holds. And this is the problem that can be solved by studying this structure, and this structure leads to differential calculus and the notion of derivative. So from next video we will start with derivative. So you are happy at the end, you wanted derivative, and so we will study them. Opens the road to differential calculus. Okay, see you.